Very much. Already pleasure to be introduced by you. So my name is Valeria. I'm going to introduce myself a bit more later. I just wanted to give you like a brief agenda. Why am I even talking about what I'm going to talk today and sequential bootstrapping finance? I'm going to show you why financial data is actually not really a plug and play thing to just blindly use a lot of machine learning algorithm on it. What are the problems and how we can kind of lessen the effect of imperfectness of the financial data and make it more suitable for machine learning, and basically a lot of different approaches of how we can fix the issues, right? So as the title says, we're going to be discussing sequential bootstrapping in finance, what it is, why do we need it, and how it's different from regular bootstrapping. And we do so to approach the true IID sampling. So, as I said, my name is Valeria PERVUSHYNA. I'm a quantitative researcher at Hudson and Thames and master's in quantitative finance at the University of Warsaw. If you'll have any additional questions after our Q&A session at the end of my lecture, you can reach out to me via social media handles on Twitter. Yet I'll have my LinkedIn mentioned also at the ending of this lecture. So if you want to chat, I'd really love to do it even after those lectures, and I'll be glad to connect with you. So, right, let's see what the agenda will be for today. We'll start with the acknowledgements of and the main inspiration for this lecture, and move on to talk about the data limitation in financial machine learning. Why does bootstrapping sounds like a perfect solution for it? And what are and we're going to talk about one of the core points of all of the machine learning, assuming the IID of our samples, right? And after that, we're going to talk about what happens if the assumption of the IID is in fact not true, which is usually the case in finance, and give a more of a detailed example and close to real-time issues, the issue of the overlapping outcomes, and also the concept of concurrency, which is going to be one of the centerpieces of our approach. Right. After that, we're going to talk about 3 possible solutions for label uniqueness, and the deeper discussion will be held around the sequential bootstrapping being one of them, and in my humble opinion, the best one of them. We'll also discuss the mathematical definition of the procedure and how it actually works. Talk a bit about these empirical results and comparison between the regular bootstrapping and the sequential bootstrapping, right? And kind of conclude everything with a short and concise conclusion. Also, all the references will be mentioned at the end of the presentation. So that's about what we're going to be talking today. So I'd like to first and foremost give credit where credit is due to the key inspiration for this lecture, the book by Professor Marcos Lopez de Prado, Advances in Financial Machine Learning. I'm sure a lot of people heard about it or read it, and it's an incredible piece of work that inspired a lot of professionals in the field and introduced a lot of concepts that were groundbreaking for a lot of people. And I just want to say that we at Hudson Thames really admire the work of Professor Marcos de Prado and are inspired by him and actually implement a lot of his approaches in our products. So first and foremost, credit to Professor de Prado for being the key inspiration for this lecture. And I'm going to cite him quite a lot during this lecture, so I hope you bear with me. Right. I have to start today's discussion about the data in financial machine learning with talking about its limitations. One of the biggest constraints in quantitative finance is actually how limited the historical data, financial data is. A lot of the assets don't have any history past like 2010, and even less of them past the year 2000. However, the universe of assets is so vast and so big, which actually, with combined with the scarcity of historical data, results in a lot of problems regarding financial machine learning. For example, the curse of dimensionality results in sparse data, overfitting, right? Not really cool stuff, because, for example, for something like voice recognition, you can create an infinite amount of voice samples and be good with it. But with financial data, you're limited with the history you have. And the fractionality is also kind of limited because the high frequency data, right, was introduced not that long ago, which relatively not long ago. So there's a lot of kind of itsy bitsy problems that combine into bigger ones regarding the overfit in financial machine learning. So the natural solution to the data scarcity would be bootstrapping, which is a natural way for a machine learning specialist to think about enlarging their data pool and kind of preventing the overfit and kind of trying to tackle this data, as it allows to generate new samples from an already existing data set. As you can see neatly displayed on the right-hand side, we have our training sample, and we generated a bunch of bootstrap samples, randomly picking data from our training sample, and kind of wrapped everything up with our ending ensemble classifier at the end, which is our way to kind of combat the lack of actual data in a training sample. And to quote, under certain conditions, such as larger sample sizes, the sample distribution will be approximately normal, and the standard deviation of the distribution will be equal to the standard error, which is actually very good for us, and yay is the way to go. And seemingly, the problem is solved. But this is not really the case. And to preface the main problem itself, I'd like to talk about the core assumption of machine learning in a lot of the data science, assuming the IID of our samples. And the phrase assuming our samples are independent and identically distributed, I'm sure you've seen it countless times at the beginning of almost every research. And in fact, it's used so often that saying it at the beginning of your research almost becomes habitual, right? And just like a force of habit for a lot of professionals. And I don't blame them, because indeed, this is a core assumption that allows to create generalized algorithms that are performing well out of sample, and is essential for such core theorems in data science as central limit. Central limit theorem and the law of large numbers. And yes, for face recognition, voice recognition, spam classification, or fraud detection, it's a no-brainer assuming the IID of the data. That's completely okay if you're doing it. Most likely you'll be right, and you will not be making any kind of crucial mistake. However, in financial data, unfortunately, this is not the case, because the data leakage and the information leakage between the samples is actually a very big deal. And to kind of more visually and more clearly demonstrate what the problem is with financial data, I'd like to use the example provided by Professor DeBrada in his book, and we're going to talk about blood samples and what happens if the main assumption is not true, right? Imagine we have these 5 samples from 5 different people, and we are measuring the cholesterol level, right? Because the samples are distinct, we kind of clearly can distinguish what features of what person, what features of those people are actually taking more of the weight in determining the high level of cholesterol. But imagine somebody in your laboratory spills blood from each tube in the following tubes. Now you need to determine the features that are impacting the high cholesterol level without knowing the cholesterol level of each exact patient, right? And this is becoming a ridiculous and a very hard task, because now this is actually equivalent to what we have in financial data, right? With the additional handicap in financial data that the spillage pattern is non-deterministic and unknown. We don't know which fraction of the blood spilled to the other vials. But there's no such thing as unsolvable problem. And as we start diving deeper into the financial side of this, the issue of the overlapping outcomes and application actually to financial machine learning, we'll see how can we try to combat this issue. So first, we can see that on the right-hand side, you can see the visualization of the issue of the overlapping outcomes. So assume the outcome yi assigned to a feature xi is a function of price bars that occurred over the interval ti0 and ti1, right? So let's think of some concept, for example, meta labeling, not meta labeling, but triple barrier, right? Triple barrier is dependent on some time horizon, time window. In our case, this is our time bars window. The next label that you can see that will be yj will be dependent on a window that is actually has some overlap with the previous outcome. And now the series of labels yi with I from 1 to I capital are not independently and identically distributed, because there's an overlap between those consecutive outcomes, and it actually screws up the independence of the whole bigger sample. The overlaps can differ, right? We can have this like kind of consequent overlap. We can have that, or previous outcome will have this data bar window of the next outcome kind of encapsulated in itself, and they're very, very, very different variants of how the overlap can happen. And I think most of people will think like, why don't we just restrict the horizon? Why don't we just restrict the overlaps? But unfortunately, it actually doesn't give us the result that we want. First and foremost, it leads to coarse models and actually renders the usage of techniques that we actually wanted to use, for example, like triple barrier labeling, useless, because triple barrier specifically requires the possibility of such overlaps happening to actually be possible to use. So we need to think of a different way to solve this problem. And before talking about solution, we're going to introduce the concept of concurrency. We say that two labels, yi and yj, are concurrent at the time t when both are a function of at least one common return. So in this case, we have our yi and yj, and they are dependent on this overlapping return here, right? The opposite characteristic to concurrency is called uniqueness. And what we're basically aiming to do is to increase the uniqueness of our sample. This is our goal. And how can we solve this problem? We can do it in 3 ways, right? First, we can do the most basic and like brute force-ish way, is to just drop overlapping outcomes before performing the bootstrap. But it is actually not a great way to do so. It leads to a ton of like a huge loss of information. It basically does you more harm than good, right? You can do it in a more accurate way, utilizing the average uniqueness to reduce the influence of the outcomes that contain redundant information, right? But still, it's not ideal. It's kind of trying to judge everything by one average characteristic, and still results in more of an information drop that we would like to. And the third solution, which we're going to be talking in more detail today, is performing a sequential bootstrap, where draws are made according to a changing probability, which will be controlling for redundancy. And as we know that during the bootstrapping process, incorrectly assuming the IID draws leads to oversampling and becomes increasingly likely that our in-bag and out-of-bag observation will be very similar, so making the whole process redundant. So our usage of sequential bootstrap tries to kind of combat exactly that, right? So how does sequential bootstrap work? What is the main idea for the sequential bootstrap? The idea is we want to reduce the probability of drawing the observation with a highly overlapping outcome, and we're going to try to control it on every step, on every draw. We are achieving this by updating the probability for draws, for drawing particular values for each new draw based on the uniqueness calculated using the sequence of previously made draws. Right, so with each step, with each draw, we are recalculating the probabilities of drawing the highly overlapping outcome, and after that, we're drawing the next. We're performing the next draw for example. So let's talk about mathematical definition. The key advantage, first and foremost, of the sequential bootstrap is that overlaps are not impossible, right? And even repetitions are not impossible completely, but they are decreasingly likely. So we're not excluding the information, we're just trying to control for uniqueness, which is the greatest, I think, accomplishment for this technique. We're not, by not excluding this data completely. Let me go in bit with detail of the notation. Our capital I will be the number of items in the initial set. The phi is the sequence of draws so far, and the I, sorry for the name, is uniqueness of drawing I at time t. So the procedure looks as following. In general words, as I said, we're basically trying to control for the probability of drawing the highly overlapping outcome with each draw. But first, the first observation xi is drawn from a uniform distribution with the original probability of drawing any value I denoted as delta I. So it's basically 1 divided by the number of items of the initial set. Will be our initial probability. After that, to reduce the probability of drawing the observation xj with the highly overlapping outcome, as we saw in the concurrency slide. So we want to kind of reduce the probability of drawing this outcome with the overlapping returns. We calculate the uniqueness of drawing j at time t metric, right? We're having this identity matrix, and we are multiplying this by 1 divided on this sum, right? After that, we're going to calculate the average uniqueness of drawing j at time t over j's whole lifespan. So the lifespan is t capital, and we are calculating this average uniqueness like so. And a second draw after that, then it's based on the updated probabilities delta G2, which we have our average uniqueness, right, divided by the sum of the all average uniquenesses for all of our items in the initial set. And after that, this process is repeated until I draws have taken place. So basically, we have this type of cycle going on. And this is basically the whole procedure. The key point for us is that we are reevaluating our next the probabilities for each and every next draw, which yes may take some time. However, it will control for uniqueness in a much more significant way than any regular bootstrap will do. So about the results, just to show you that this is not any only empty words. I have shown you here the result from the book, from the Advances in Financial Machine Learning, and we also at Atom team performed the experiments ourselves and came to almost like identical results, very similar results in terms of magnitude of difference. So we have here the Monte Carlo experiment of 1 million iterations of standard on the left-hand side and sequential bootstrap on the right-hand side. And we can see that the median value for the uniqueness, this is the scale for our uniqueness, for the standard bootstrap, the median uniqueness is less than for sequential bootstraps. And we can say with confidence that statistically speaking, samples from sequential bootstrap method have an expected uniqueness that exceeds that of the standard Bootstrap method at any reasonable confidence level, which is, in my opinion, great. And I am very happy that we were able to improve the situation with the uniqueness in a significant way with sequential bootstrap. So as a conclusion, I'd like to say, well, there's no perfect cookie-cutter solution for the overlap problem in financial machine learning. The sequential bootstrap allows to efficiently and reliably increase the uniqueness of the labels, providing a big improvement in the quality of the bootstrapping process. The references are stated in the slide. You will be able to access the slide after the lecture, I believe. And also, if you would like to use those bootstrapping procedures on your own, we have at Hudson Thames, they are available in our MLFinLab package. They're ready to use, and all of the mentioned algorithms, as well as many more from the professor as well, are available in MLFinLab package. They are available as very easy to use, already created, well-documented functions, and are packed in the Python library that is called MLFinLab. So if you're interested, I highly recommend you to check MLFinLab out on the Hudson and Thames page. You can just get it self-serve if you are interested. All right, so I think that's it for the lecture part for me, and I thank you very much for your attention, and I'd like to answer all of your questions if you have them.